titled System Engineering Design on Strategic and Non-Strategic Machine Tools as Applicable to Electrical and Electronics Engineers by Dr. Wasim Ahmed Khan, who has graciously joined us today. This webinar is brought to you by IEEE PAF-KIET Student Branch and IEEE MUET-SZAB Student Branch collaboratively. We are extremely delighted to have Dr. Professor Wasim Ahmed Khan with us today, who is currently a professor in the Faculty of Mechanical Engineering at GHULAM Khan Institute of Engineering Sciences and Technology. He is also the director at Office of Research, Innovation and Commercialization, senior advisor at the Catalyst, the GK Institute Incubator, and the coordinator at GK Institute Professional Education Program. He has done his PhD from Department of Mechanical Engineering, University of Sheffield, England. He is also a life member of PAC, Chartered Engineer of the Engineering Council UK, Fellow of the Institution of Mechanical Engineers UK, as well as Senior Member of IEEE USA. He is also a member of IEEE Computer Society. His research interests include virtual reality, virtual manufacturing, operations research, and education management. Thank you very much for joining us today, sir. Before we begin, all our participants are requested to keep your mics and videos turned off during the entire session. We will have a question and answer session in the end in which you can raise your hand and the host will give you the opportunity to ask your questions. You can also send any questions or messages to the host through the chat with your name and affiliation at the end. Please be attentive during the session as there will be a short and easy quiz at the end which will be sent to you through email along with the recording of the webinar. You will have 24 hours to attempt the quiz in order to be eligible for the certificate. The certificates will also be emailed to you within 1 week from today. Now, without further ado, we'll hand over the controls to our most esteemed speaker, Dr. Wasim Ahmed Khan.
Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. I hope all of you are doing well. I'm Dr. Wasim. As Fabiha introduced me, I'm not going to take more time introducing myself. I'll just continue with the seminar. Today, I'm going to give you a talk on electrical and electronic aspects of machine tool design. Next slide, please. The agenda of the talk, I will give you an idea about the functional reverse engineering. What is it about? I'm going to talk about strategic and non-strategic machine tools, the system engineering design, the connecting variables, the type of motors, the range of microcontrollers, the sensors and transducers, the black box for us, and I will tell you why for us when I come to this particular point. Iteration for selection of component for system engineering design, circuit design using Proteus, Multisim, and other software packages. Similarly, printed circuit boards for design using different kind of software. Next slide, please. Okay, the functional reverse engineering basically is a redesign technique that may augment configuration, orientation, and bring innovation in discrete products. You must be wondering what is a configuration, what is the orientation. I'm displaying, an object that you might not have seen it before in your life. Okay, this is a machine tool that I'm going to talk about in detail. It comes from an international standard, ISO 841-2001. This particular standards gives details of this particular machine, which is called the vertical turning and boring lathe. Okay, in this particular vertical turning and boring lathe, the configuration is how different components are placed, like this rotary table, like this particular component where we mount the tool, and so on and so forth. And then we have the orientation. Orientation is the axis in which this particular machine is capable of moving. Okay, There are a number of things, which are marked here, like U, W, R, and so on, and P also. Okay, I'm sure you know the primary axis. You learned this thing in your seventh class. Okay, you learned the right hand rule. Okay, so we have the primary axis, which is the X, Y, and Z axis. Then we have the secondary axis, which are called the UVW. I'm sure you have used the vernier caliper. And vernier caliper, you have you know major axis, major measurements and the minor measurements. Okay, so if X is the capital X is the basically the major axis, then U is basically the minor axis. So similarly, we have the X, Y, Z, the primary axis, the U, V, W as the minor axis along with XYZ. And then we have the rotational axis A, B, and C. And C is here, if you can see it over here. That is about Z axis, rotational axis, that is about Z axis. And then we have the PQR, which are the tertiary axis. I don't have time to explain all of these things in detail, but if you refer to the standard ISO 841 2001, you will be able to find the detail, how these particular things are explained. Okay, next slide, please. Okay, the manufacturing is a complex science. Okay, according to Kalpakjian and Schmidt, they are, two professors from USA. Okay, they have written two books on this particular topic. One related to the manufacturing technology, the another related to the processes for manufacturing processes for processing different type of materials, and they have given a classification, and this classification is as per forming processes, bulk deformation processes, and so on and so forth. I'm not going to read the list. You can read it yourself, and over here I will just give you some example. The machine that I just showed you, okay, the vertical boring lathe. Okay, we had that was one of the metal removal process. Okay, which is a subtractive manufacturing tool in which we remove the material from the we remove the material and we subtract the material. Okay, in contrast to that, we have additive manufacturing processes, which is the current trend. And in future, all the manufacturing processes, after 30, 40 years, 50 years, okay, we are going to have all the manufacturing processes in the form of additive manufacturing. Today, I'll give you an example and I'll show you an example of both metal removal processes, the subtractive manufacturing processes, and the additive manufacturing process. I'll show you these things and I'll show you how these processes are basically, have what type of configuration they have, what type of orientation they have, how can we have the augmented reality of these things, how can we have the IIoT of these things, and so on and so forth. We are going to talk about it in detail in a while. Next slide, please. Okay, just for a while, I have to shut down my video because one of the machine is being hidden by the picture. Okay, so I just switch off my video. Okay, I was referring to this standard ISO 841 2001E. This is the most latest standard that you find about the subtractive machine tools and different kind of machine tools. Okay, I am showing you two machine tools. One of them is parallel lathe and another one is a twin turret lathe with programmable task. Okay, why I'm showing it, I talked about the topic of the whole webinar is the system engineering design of strategic and non-strategic machine tool. So we have to define what is a strategic machine tool and what is a non-strategic machine tool. So the strategic machine tool is basically a machine tool that can produce any discrete product, including non-strategic machines. Okay, the discrete product, again, this is a new concept here. The discrete product is basically a product that can be counted. So you can imagine that in world there are billion of products, those can be counted. Okay, so I'm showing you here, these are the two strategic machine tools which can produce any discrete product, including non-strategic machine to non-strategic machines. Part of them, assembling them, we get a non-strategic machine tool. Next slide, please. Here I have the example of non-strategic machine tools. Okay, these are the machines those produce food, shelter, apparel, and other items of general use. Okay, I'm showing you two machines here. One is the milk packing machine, another is a wheat thresher, which basically gets you out the grains of the wheat out of the crop that you have. Okay, now the components made here are basically from the manufacturing processes, using the manufacturing processes, the classification of which I have already given you at the earlier slide, which I have taken from Kalpakjian and Schmidt. Okay, and most of them are basically the subtractive manufacturing processes. So these are the machine tool which gives you, for example, this machine gives you the food. This machine also indirectly provides you food. Similarly, you can have machines which are used for making the shelter, like for example, uh, you know, uh, 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 let me find you uh, a concrete mixing machine, that helps in building shelter, the textile machinery that used in the apparel, and there are a number of other machines those can be used for other items. Next slide, please. Okay, what is system engineering design? We say in our topic, this is the system engineering design of strategic and non-strategic machine tools, electrical and electronic design perspective. Okay, now you know what is the strategic and non-strategic machine tools, and definitely we're going to talk about the electrical and electronic design perspective. But let's talk about, okay, uh, what is the system engineering design? Okay, the system engineering design involves number of things. Okay, you basically have to perform the mechanical engineering design aspect of the machine. You have to perform the electrical engineering design aspect of the machine. You have to work on the electronics engineering aspects of the machine. So basically, my topic today is mainly I'll focus on two and three, not in detail, a little bit, okay? But then you also have at number four, computer hardware engineering aspect of the machines, the computer software engineering aspect of the machines. I will comment a little bit about it, and then you also have to look into the control engineering aspect of the machine. Then there are certain features known as RAMs: reliability, availability, maintainability, and safety of the machine. These are the features that a machine tool must have. Then we have to have ergonomics of the machine, the man-machine interface, MMI, the HCI, the human-computer interface, and other parameters like where you place, like for example on a wheat thresher, where would you be putting in any kind of sensor or transducer, and so on and so forth. Like for example, one of the other parameter will be how the lighting will be in the room where you're performing a strategic machining process, or like for example, what would be the size of a handle that a Pakistani man or woman can handle, can hold. Okay, next slide, please. Okay, now talking about that, we are still explaining the basically we're still explaining the system engineering design of strategic and non-strategic machine tools, electrical and electronic design perspective. We're still explaining the topic itself. Okay, we have explained the system engineering design in the previous slide, saying that this particular operation requires analysis from all particular angles that we can think of, and we define the strategic machine tools and non-strategic machine tools, and we are going to come on to the electrical and electronic engineering perspectives. What is the system engineering design to production life cycle? If you have performed the system engineering design, that means that you have done the electrical, mechanical, electronic, computer software, computer hardware, and all the list that I showed you in the earlier slide. Then what is next? Okay, we do the design documentation. Okay, then there are design documentation is basically, is there. For mechanical engineering is different. For electrical engineering, these are the circuits diagrams that we're talking about. For electronic engineering, again, we are talking about circuits. Okay. Then we do the simulation. In, for example, mechanical engineering, we perform simulations using packages like Creo, like SolidWorks, and so on and so forth. Simulation of electrical electronic circuits is performed. Electronics, for example, Proteus, Multisim, and so on and so forth. You can perform the simulation of your circuit. Then you make a physical model for the testing of it. It can be a raw model just on a breadboard and so on and so forth, just connecting the basic component together, testing it. Then you have to do the prototyping. Okay, a prototyping would mean that you're making a physical model. Okay, that will be, in case of electrical electronic design, a real physical PCB, printed circuit board. Okay, then you look at the pilot production. When you need in quantity, you need that particular PCB, and in mechanical terms, I will explain in a minute. Okay, a pilot production, what would you do? What would you do is this, that you set all the parameters, what kind of resistor, capacitors, you think of any resistors, capacitors, and the number of other components that you require in your electronic circuit. Are they available? Are they properly placed? So on and so forth, where they're required to be placed, what kind of robotic operation is there, and so on and so forth. That is the pilot production. Okay, with pilot production, you need a lot of documentation, which in real term, for example, the quantity of a particular component, the number of the place where it has to be there, and so on and so forth. You get it, and you move forward. Then you do the production documentation. This is what the requirement of the components, that are they available or they are not available in particular quantity. This is the production documentation, and then you get into the production. That is the final stage, then where you produce hundreds and thousands of PCBs, and you move forwards. I explain this in terms of mechanical engineering, for example. In system engineering design, for example, you perform the mechanical engineering design. In design documentation, you basically come up with the mechanical engineering design drawings. Okay, these design drawings are called the first angle projection, third angle projection drawings. Okay, tolerances of the that you may have, the different kind of material that you are using in that particular component, the simulation of the part. Okay, that, as I said, using Creo, in case of mechanical engineering design, that you make a physical model. When I said physical model in electronic on a breadboard, we make the mechanical model in using wood, using plastic, and so on, so forth. In prototyping, we take it to the like electrical and electronics. I said you make a PCB. In mechanical, you would go to a a metallic model of it. In pilot production, you will take it to, a particular aspect, where you will say that I'm going to make it to the true scale of the machine, the exact machine. And for that machine, what would be required? Okay, the stores, what type of components will be required, what kind of documentation of it requires, should be the parameters, like what type of human resource would be required, what should be the qualification of those human resource, what kind of payments we have to make. You have to, all these documentation are part of the production documentation. This applies to electronic components as well. And then we go on to the production. I hope I explained it clearly. Next slide, please. Okay. Factors, those need to be considered. Okay, why are we doing all this? That is the first thing, that we must know. Okay. We are next 11 country. Okay. We are next 11 country. Next 11 countries are a group of countries which in by 2050, I guess, would be like BRICS nation. Okay, which is the another group, including Brazil, Russia, India, and so on and so forth. Okay, and which is the next layer, which is next group of country after USA, UK, and so on and so forth. There are hundreds of countries in the world, and we are safely at a place where, if we play it right, we may be an advanced nation in 30, 40 years time. Okay, for that, we have to specially get into the type of technology. We have to know how to produce the technology. Okay, and the most important technology that we must produce is the machine tools of all kind, strategic machine tools and non-strategic machine tools. I'm not saying that you only produce machine tools related to subtractive and additive manufacturing. I'm saying produce strategic machine tools and non-strategic machine tools. They may be of any kind. They may be, oil and gas drilling machinery. That they may be, biomedical devices. They may be, you just agricultural machinery. I can give you a number of examples, but all of these machinery should have a general purpose factors, which are that this machine that you're producing is economical. Okay, which means that it works, number one, and then is cheap. If you buy it from the market, from the overseas market, it basically is expensive for us. We have to pay the price in dollars, pound sterling, and other foreign exchange currency, putting pressure on our foreign exchange, uh, whatever foreign exchange we have, putting pressure on that particular account. Okay, so that machine has to be economical. And then there is another problem. Most of these machines have embargo. Okay, if we want an advanced machine, the advanced countries would not give it to us. Okay, the second thing would be, if we do somehow bring it to Pakistan, then we will have the after sales service problem. We will not be able to have after sales service. We will not be able to have the training on that machine. And then we will be doing, basically we are getting into another circle of problem, which eventually lead us to that after spending a lot of money, we are not able to use that machine to its full potential. So when we are making this machine in Pakistan, okay, this machine is economical, after sales services available within Pakistan. You can have training as many times as you like, and I will show you videos. Those can be used by anybody, anywhere in Pakistan or anywhere in world, to train themselves, on those particular machines without any problem. Okay, then we talk about the accuracy and precision. The machine that we are, the factors, one of the factors is accuracy and precision. Okay, the machine that you produce should be accurate and precise. Okay, the methodology, excuse me, the methodology that we should adopt is basically the system engineering design and manufacturing. The system engineering design I've just defined, and the manufacturing is not the scope of this particular talk. Okay, but again, there are methods of manufacturing. Okay, that includes all different aspects of system engineering design, like design, manufacturing mechanically, manufacturing electrically, manufacturing electronically, and so on and so forth. And then we have to have certain component selection. There are certain things like, for example, when you uh, talk about a machine tool, you are not really manufacturing everything. Let's say, for example, machine tool, we don't machine tool industry look at different things, like the structure of the machine tool, how to produce that, the controller of the machine tool. They do not look at the bearings, they do not look at the gears, they do not look at the electronic components, they do not look at the microcontroller, which microcontroller you're using, they buy, or which national instrument card they're going to use. Okay, they just buy it off the shelf and use it there. So there is, basically component selection part as well. I'll give some more comments about it as well. So this is, you have to make a robust design which has a part of component selection as well. Okay, and these particular robust component selection basically is iterative. Okay, you have to somehow adjust it. I will talk about it in a minute. Next slide, please. Okay, my example today is an additive manufacturing process. Okay, it's called the electro-hydrodynamic jet processes. You might not be aware of this machine. Okay, this is a research machine. Okay, it's not really manufactured widely in world. Okay, it's a specialized machine because it produces a product that is used to do certain thing which are sensitive in nature. Okay, and I will explain that in a minute. Just look at the structure of the machine tool itself. Okay, it's a small machine, it's not a huge machine. Okay, we have a clamp, we have certain stepper motors. Okay, we have the x-axis assembly, y-axis assembly. So you can see the configuration. This is the configuration, and you can see the orientation as well, that where is the x-axis is this thing, the y-axis is this thing, the z-axis is this thing, and there is a fourth matter which puts down the nose and glider assembly. Okay, which basically provides you a droplet on demand, or a continuous droplet of ink, and I will explain that in the next slide. Okay, next slide, please. Okay, the next slide is basically not the product, it's just the process flow diagram. Just please show the whole slide. Okay, continue, please. That's it. Okay, okay, this is the process flow diagram. Okay, this is the process flow diagram of the EHD jet printer. Okay, uh, what is happening, that you have a substrate. Okay, you have a table and you have a nozzle. You have a voltage amplifier. Okay, and you have charged the substrate table, and there is a very high current passing through the nozzle and the substrate table, and that basically because of the ink that is either copper based, silver based, or gold based, or whatever material that you're going to use, and you are basically performing that. Can we go to the previous slide, please? Okay, well, this is the substrate table, okay, and this is the nozzle assembly, okay, and we are not showing any amplifier here. We are not showing is any pressure generation. There is a high pressure assembly as well, which we are not showing. Okay, next slide, please. Okay, but if you just I next slide, please. Okay, if you just read it, I give you a minute to read it. Okay, there's no point I read it for you. Okay, there's no point. I just have to explain this to you that we have a process that is used for two purposes. The purpose number one is that this defines the operation of the electro hydrodynamic jet printer. Okay, number one, and number two that we have is that this helps us defining the developing the software that is going to use. There's a mention of high voltage amplifier, there's a mention of a pressure regulator, there's a mention of a nozzle. Certain pressure is applied to it that causes basically the uh, ink to flow in the form of droplets, or ink to flow in the form of a continuous flow. Okay, so what we make out of it. Okay, I think before I can we move to the next slide, please, so that we can see what we make out of it. You can easily buy it from the market. Okay, but for sensitive application we cannot buy it. Okay, what it does, first of all. Okay, what it does, this is basically a resistor, as simple as that. Okay, it is used in a Wheatstone bridge. Okay, and the four resistors, out of four, one is replaced by a strain gauge. Okay, and it is placed on a specimen. Okay, uh, to gauge the level of stresses on that particular component. And this may be a rocket motor, it may be aeroplane wing. It can be, there may be number of sensitive application for that. Okay, so I'm sure you understand that we can, how can we go ahead with this particular type of product. Okay? So the Wheatstone bridge, when the pressure is applied. Okay, when the for example, the pressure vessel, or a rocket motor expands. Okay, this particular resistor, or the strain gauge elongates, changing its resistivity, leading to the voltage difference in the Wheatstone bridge. That voltage difference is an indication of the stresses applied on that particular component. And this is what is we need. Okay, this is as the part of the analysis. Analysis on mechanical part is performed using three methods. Okay, one is called the analytical method, which is using equations. The another one is called the experimental. Okay, this is one of the experimental method. The third one is the numerical, which is using different computer aided engineering packages, like for example, we have you know finite difference method, finite element method, and boundary element method. So that is not relevant here. It is just this particular object that I'm going to show you. This is a strain gauge, part of a Wheatstone bridge, which is used in experimental stress analysis. And it is, if it is simple thing, you can buy it from any bazaar in Rawalpindi or Karachi or any big city. But if you need a precise output, if you need a sensitive application, you have to give an end user application, and import of it is restricted. Okay, so this is something that is, what we do. Next slide, please. Okay, we go on to the next thing. Okay, you have seen the structure of the motor, the process flow diagram, the product, the application. Now it is a simple thing for you. Okay, I'm sure you understand. You have to use a microcontroller. You have to use a stepper motor driver. You have to have a stepper motor. Either way, it can be a different type of motor as well. It can be a servo motor as well. Then there is a mechanical system. Okay, that you have to rotate. Okay, next slide, please. Okay. Uh, okay, it is a NEMA standard motors that I'm talking about here. It can be other type of standards as well, not necessarily NEMA, but basically what you're looking for, that NEMA 17, 23, 34, 42 type of machine, depends on the type of. Now you must understand, what do I mean by configuration and what do I mean by orientation. Configuration basically gives you the structure of the machine, that how it is, the different parts of it, the x-axis is placed, the y-axis is placed, the z-axis is placed, how the nozzle is placed, and the process flow diagram, the process itself is basically slightly different. Now I'm going to give you, if I had been in a classroom, I would have drawn it on a blackboard or whiteboard. Okay, but you have to understand this particular system. You have to understand something, very clearly. All engineers know it, very, I mean, especially control engineering student understood it very well, that everything is basically an input process output methodology. Okay. Now what we can have, we basically embedded process as well. One process embedded in another process. Okay. Now what I will say, that the embedded process in this particular case is the mechanical process, which gives you x, y, and z movement. Okay, and the outside process, which is embedding the mechanical process, is the electrohydrodynamic process, which basically provides you the process flow diagram which you have to implement. Here I make some comments about the software. You have to move the motors, you have to write an interpreter. Okay, you have to make sure that these motor signals are given to these motors. Okay, and they can move in x and y direction. The component that I have shown you, the product strain gauge that I showed you, basically is a two-dimensional object. Okay, it's not in z direction. It's a very thin layer. Okay, and basically we're talking about having having you know embedded process, and the outside process is the process which is the process which is shown by the process flow diagram. And you have to write software which basically combines the mechanical process and the electrohydrodynamic jet process, embed it and get it, and that process should move these motors working on a particular torque so that they can move, and so on and so forth. Next slide, please. Okay. Uh, Drivers. Okay, you understand that as well. I'm sure you understand that to drive a motor, you basically need a driver. To run that motor, you need a driver. Okay, you have NEMA 17. It is 1.7 ampere per phase, and so on and so forth. The values are written in front of you. Okay, you can read it. Driver is selected based on current requirement of electric motor. Okay, this is the basic rules, and you have to basically match. What the comment that I have to make basically, you have to match the specification sheets. Okay, like the specification sheet of the NEMA motor, and then you have to match the specification of the driver, okay, of the driver those are available. Okay, and the other thing that you might have to burn a few of the drivers before you get to the final stage, because it has not necessarily you are getting to the perfection at the first stage. Okay, and there are methods, basically the simulation done by the Proteus and Multisim or other packages. Okay, basically provides you the different type of values. Okay, which can lead you to select a particular driver. But again, if you're not careful, you are going to burn uh, 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 the driver. Okay, next slide, please. Okay, the drivers, basically there are a number of drivers listed there. This is not all the drivers. The slide can fit in only 5 drivers. The details are basically given by them, and no mention of other type of motors. Okay, this is a simple thing that is a matching of different kind of specification sheets, a bit of electronic circuitry development using multisim and these softwares. Okay, putting most of the time adding these particular drivers to those softwares and so on and so forth, and eventually trying to optimize the whole PCB. The next slide, please. Okay, the microcontrollers. Okay, the microcontrollers, the selection criteria of a microcontroller is based on that how many input output lines do you need. Okay, what kind of memory it has, and what kind of processes you can control using a particular microcontroller. We have tried, being an education institution, we have tried almost number of microcontrollers. Next slide, please. Okay. A few of them are at Mega Arduino boards, Raspberry Pi, STM32, BeagleBoon Black, Dragon board, and so on and so forth. PIC is not mentioned here, for example, and there are other boards as well. You can always look into national instrument cards too, which can provide you with some kind of functionality, and so on and so forth. Next slide, please. Okay. The circuit design. The circuit design. Okay. Now the drivers, uh, the microcontroller, uh, the sensors, the transducers, the fuses, the resistors, the capacitors, the cable, the heat sinks, the whatever components which are used in the circuit have to be optimally placed, designed. Okay, which is an artistic thing. Okay, which is something that you have to do. That is something that you have to perform. Okay, so we use these Proteus and Multisim commonly to design the circuits and develop the PCBs that we use. We use some more software. Next slide, please. This is the circuit for the EHD. Okay, there's not much that is just for display. Cannot be. Next slide, please. please. Okay. Uh, okay, the PCB design, that is the most important thing. Fritzing, Altium software, those are also gets involved. Okay. And, we design the PCB. The cycle of production is the same thing as I just described earlier, and you use those particular things. Next slide, please. Okay. uh, Once you have developed the product, okay, at every stage you have to perform certain type of quality control. Okay, once you have certain level of quality control, when the product is being produced, normally, then you get into the quality assurance. You don't check every single product. You check, 10 after one after 10 products, or one after 20 products, or one after 30 products, and you continue with that. Okay, so this is something that that is important. And once you have assembled the machine or the whole thing, you have to calibrate it. You have to calibrate it. You have to make sure it is performing the function that was intended. Is giving you the efficiency. It is giving you the accuracy. It is giving you the factors those I mentioned in an earlier slide. Next slide, please. Okay, please run the video. This is just a model, okay, of electrohydrodynamic machine. Okay, I'll show you some machine from my own screen. Okay, this is the x-axis, this is the y-axis, this is the nozzle. This is just a model made in wood. Okay, and so on and so forth. The three motors that we talked about, the X, Y, and Z motors. There's no motor for the manual control of the nozzle and so on and so forth. Next slide. It's not much interesting. I'll show you an interesting. Okay. The acknowledgements, the acknowledgements to the GIK Institute undergraduate, graduate, and postgraduate students. My co-investigator, Dr. Ghulam Abbas, Dr. Ghulam Hussain, Dr. Khalid Rahman. Dr. Khalid Rahman basically specializes in additive manufacturing, okay? And this is basically his work that I was presenting, okay? Of course, the GIK Institute of Engineering Sciences and Technology that gives us the opportunity to work on these things and the liberty to work on these things. Okay, that is thanks to GIK Institute. The Abbasin Techno, okay, it's a place where I'm going to show you some video. I do some consultancy here, and I'm going to show you some video sharing my screen. Okay, that was developed at Basin Techno. This whole grant, as I said earlier, basically is given by the federal government. We got around 100 million Pakistani rupees, okay, and that was a federal government intervention given to direct government of Khyber Pakhtunkhwa, that goes to Directorate of Science and Technology, and we competitively win it, and we are working on it. Okay, next slide. Okay. Uh, Either you can have questions, or you can let me show you some more machines, and after that you can have some questions. If I can
So we
share
can
the.
you can share your screen with the videos,
Okay.
and then we'll have questions at the end.
Okay. Let me show you. Can I share my screen?
Yes, sir, you can share.
Okay. Can you see my screen? Hello. Am I audible?
Yes, sir, you are audible, but not screen share.
You cannot see my screen. Okay. Let me Let me go to the screen share. And you have to allow me to share my screen.
Rahman, have you changed the setting?
Okay. I got it. I got it. Now you will be able to share. You will be able to see my screen. Okay. Now you can see my screen.
Yes, sir.
Yes, sir.
Okay. This is an augmented reality. I will rerun it. Okay. This is a video which is about to finish. Okay. This is one of the machine that we
Sir,
developed.
your video is still loading. It isn't visible right now.
Uh, yeah.
It
Okay.
takes
Okay.
at least 2 to 3 minutes to load.
Okay. Okay. Okay.
So I think the screen sharing has stopped.
Okay, I will start it again. Actually, I have to open the particular machines. Okay, is screen sharing on now?
Yes, you can share, but it isn't visible right now.
Beta, आपने you have to transfer control to me.
So the control is yours because the settings are open to everyone.
Okay, let us try. Can you see my screen?
No, we can't see it yet.
Oh, you can't see it. Okay, well, let's try. Let's try it again. Okay, no problem. No problem. The video is running on my screen, but let me
Sir,
see my.
you have to share it from the Zoom platform. Click on the share button once again.
Yeah, that's what I'm trying. That's what I'm trying. That's what I'm trying. I'm making some mistakes somewhere. Okay. I've shared my screen, and I'll keep trying share. Instead, give me the share screen option, and keep going on with the questions.
Mm, sure. So now the floor is open to questions. If any of the participants would like to ask anything, please raise your hand and the host will unmute you. So do we have any questions? You can also mention your questions in the chat. Okay, so in the meantime, I have a question at my end. Would you mind if I ask?
Sure. You can ask.
I just wanted to know that in your particular project, the EHQ project, you use stepper motors. So is it possible to use servo motors instead of them?
Yes, of
And
course. You know The answer is very simple, beta. The answer is very simple. We are making small machines, okay,
Mm,
where the torque requirement is not very high, okay.
mm.
And you know, we are the light for lighter machines. We use stepper motors, okay, and beside it is a digital device, okay. So you know, the software is easy to write as well. So that's the answer to your question. You know, for heavier machine, we are going to use the industrial scale machines that we are going to develop now. Inshallah, we'll be using servo motors.
And there was one more question. Usually,
Mhm.
when we are developing our systems, we simulate the electronics part very easily. But when it comes
Mhm.
to the mechanical part, most of the students face very some serious difficulties.
Mhm.
We may develop the structure over SolidWorks, but at times our systems need some more testing. So can you guide us a bit on that, so that if there are any other softwares that we can use for mechanical systems testing, the working of joints and other things, if we want to test them out?
Okay, it's you know, the reason, you know, the best thing that you know is basically the formation of the team. uh, that is the basic problem, okay. At one point we here at GIK Institute having the problem generating developing electronic circuitry, okay. So we partnered with the faculty of electronic engineering, okay, and they taught us, you know, how to develop the electronic circuitry. Now we have a full-fledged electronic circuit you know, an electrical engineer who has the capability of designing and developing electronic circuitry and electrical circuitry, okay. You need a specialized person. Until such time you basically have to partnership, okay, within your you know premises, within your faculty or across the institutes, okay. You have to make partnership. This is very important, okay. Like for example, if you don't have mechanical, I'm sure PF-KIET has a mechanical engineering department. So you partner with them, okay. You make the electronic circuitry and let them develop the mechanical part of it. uh, I can tell you the design step I have already defined. You know, the answer is that you basically have to have the concept design, you have to have an embodiment design, you have to have the detailed design, you have to go for the design documentation. Then in each steps there are number of repetition. If you like, I can send you some slide by email, okay, and you can distribute that. You know, I teach that subject, so I have ready-made slides available with me, okay. That's my answer.
So that would be nice. Yeah. Thank you very much. Okay, we have a question from one of our participants, Asif Ali. Host, can you please unmute him?
जी बेटा फिर से रिपीट कीजिएगा.
We have a question from one of our other participants, Asif Ali. So, host,
Mhm.
please unmute him so that he can ask his question.
Yeah, sure.
Asif Ali is not responding.
Okay. So, in the meantime, do we have any other questions from our participants? Are there any questions in the chat?
There is no question in the chat.
Okay. So far we have another question.
Okay, and I think I'm having a problem with my, you know, screen
Screen
sharing as
share.
well. Yeah,
Okay, it's
so
okay.
uh, I would say thank you very much. Thank you for inviting me. And
Thank you, sir.
it,
Uh,
it,
we would like to share something from our end, sir. Can we do that?
yeah, sure, sure, sure.
Okay, sure. Abdurrahman, please share the screen. Okay, sir, this is a very humble token of appreciation from our side for the time
Okay.
that you have given us, the efforts that you have put in to speak at our platform and preparing the presentation and setting aside time from your precious schedule. We appreciate all of that immensely. Due to the COVID-19 situation, we are quite regretful that we can't present something to you in person, a souvenir, a shield perhaps. But we hope that you can accept this very simple and a very small token of appreciation from our side. It was truly a pleasure to have you with us here today.
I'm grateful. I'm grateful. I'm grateful, and it's beautiful. And thank you very much for taking time out to make this, especially grabbing my picture and putting it all together. Thank
Okay.
you very much. Thank you to IEEE. I think Zabist is also
Yes,
Zabist is
the
also there.
MUET. Yes, it is
MUET
from
is
a
also here.
university at Kharagpur. We have organized this event collaboratively with them. So,
Okay.
Alhamdulillah, we have had a very successful response. And it was truly a very informative session. We learned a lot from you. And we hope that if after the Eid holidays, perhaps if you find time, I realize that you're extremely busy, but we would love to learn from you again as well.
You're most welcome, Beta. I'll try to find time out for you as
Yes,
well.
sure,
For
sir.
all the
Thank
students,
you.
all students are always welcome. Thank you very much,
Thank,
Beta. Thank you very much.
thank you very much.
Assalamu
Now we
alaikum.
would also, Walaikum assalam. Now we would also like to thank our participants for attending this session and for supporting our event. Thank you immensely. Eid Mubarak to all of you. A very belated Eid Mubarak, and to some of our foreign participants here. So thank you very much for joining us today, and we hope to see you again, inshallah. This is goodbye for now. Allah Hafiz.